Hello and welcome to section 13. We'll be finally discussing the sun. If you've been following along these video series so far, then we've talked about the planets, their moons, their rings, the comets, the asteroids, the dwarf planets, basically every little thing that we can discuss in our solar system, except for the big one, the sun, the center of our solar system. So let's dive right into the material. You all know the drill at this point. New section, new quiz. So one question we're going to ask ourselves is that every second, what is happening to the sun's mass? Go ahead and pause, give yourself a moment, and be right back. So yes, every second that goes by, the sun's mass is getting smaller and smaller. We actually benefit. We are absorbing the energy released as the sun is literally throwing away some of its mass. Now, it's not going to be the throwing away of these pictures that you think here, of these plumes of material being jettisoned off. No, the mass, the energy that we're absorbing from the sun is going to be a lot more subtle and a lot stranger. So what we're going to do in this section is we're going to talk about what's the nature of the sun, talk about how gravity's trying to squeeze in, but it's got its own pressure pushing outwards, and how the sun goes about converting its mass into energy, the very same energy that we get to absorb and thrive on this planet. And we'll go about modeling what's going on in the sun's interior and work our way outwards of the sun. And we'll talk about this strange problem involving the neutrinos. What the heck are neutrinos, and why do we have this huge issue in astronomy when we had this lack of neutrinos that we were measuring? At the very end, we'll start to describe the solar cycles. The sun has a natural rhythm that goes, well, it's about 22 years long. We notice it in about half period patterns. Every 11 years, we see these upticks in activity. So just as the big picture, here's the layers of our suns, and we really only see the outer layers, and that'll be the corona, the chromosphere, and the photosphere. And I'm working my ways outwards. So corona is going to be the outer layers of the sun, chromosphere is underneath that, photosphere. On the photosphere is where you're going to see objects like sunspots. So these are about the layers that we can see. Please don't ever look directly at the sun. Please, I just can't emphasize that enough. Just don't look directly at the sun. Use tricks, use technology. I mean, look at the shadows that the sun can cast. Like, do all sorts of fancy tricks, just not with your naked eye. With that out of the way, let's start peering our way into the interior of the sun. And we're going to use physics and a lot of fancy tricks. We'll get to those in later segments of this lecture. Peering underneath those layers, we're going to have the convection zone. This is how the sun's energy is getting out of the core through a process of just convection. The hot air rises, cools off, falls back down. Underneath that is the radiative zone. And this is just where the sun's energy is wiggling its way out from the core. In here, there's no fusion processes happening. Everywhere the sun's powerhouse, all of the energy the sun's producing is only in the core of the sun. So one thing you need to think about is, have you ever seen the sun dim? You may have been outside and see, a cloud go by, dimming the sky around you, dimming the area around you. But have you ever seen the sun fluctuate? No. The sun's been relatively constant, relatively stable over its entire lifespan, which we know to be about 4.6 billion years long. So the solar energy production, the energy that's being produced by the sun, is happening at a fairly constant rate over literally billions of years. This is all due to a process described by this hydrostatic equilibrium, and this should remind you of this exact same term we use when discussing the definitions of planets and dwarf planets. It's this idea of you've got gravity trying to squeeze in, and you have this outward pressure. Think of, try crushing a rock with your bare palm, right? As you try and crush the rock, you're going to cut yourself. It's going to have this outward pressure pushing on your palms. So this hydrostatic equilibrium is when the inward pull of gravity finally gets counterbalanced by the outward pressure. And for an object like the sun or any other star, that equilibrium happens at a level where fusion can occur in the core, releasing that solar energy. Now let's look at a couple of plots of what's going on so we sweep through the interior of the sun. For every single one of these pictures, you're going to have here at the very center the core of the sun, and we're going to go outwards in solar radius units. So this will be the outer edges of the sun, one solar radius. The temperature and the density, they follow a very predictable and intuitive map here. At the core of the sun, you're going to be at the hottest temperatures, the highest densities. And as you sneak out of the core, as you go outwards, the density is going to go down, the temperature will go down. Not linearly, but it's still going down in a nice, predictable fashion. So some quick comments here about the temperature and density. Notice here, at the core, we're getting up to temperatures in our sun upwards of 15 million, that's 10 to the 6, 15 million Kelvin in the core. We're going to need temperatures like that for the fusion processes that we want to get energy out of the sun. Let's start going through these different layers. You've got this bluish, this orange, and this kind of yellowish regions. What are these? Nuclear fusion. Anywhere from 0, the center of the star, to about 0.2, 0.3 solar radii. That's where the nuclear fusion is occurring in the sun. This is where the temperatures are hot enough, the pressures are extreme enough to allow fusion process to occur. Outside of that's your radiative zone. And this basically just means where all the energy that gets produced by fusion in the core, it has to radiate outwards. And the convection zone, this is going to be starting getting to almost the surface of the sun. And that's just how that final energy literally rises up as a gas. That energy will excite gases, heat them up, and they'll rise up through convection, releasing their energy out into the atmosphere around the sun. Now let's go through the percent of hydrogen. The sun is a mostly hydrogen ball, and the amount of hydrogen is fairly constant. Any section of the sun you look at, you're going to find that it's roughly 75% of the region. A little more than 75% of the sun's whole mass is just hydrogen. But look what happens once you get into the core. Why is it dipping down? Well, it's dipping down because hydrogen is what's getting burned up. Hydrogen is what's going through the nuclear fusion processes and consumed. There's less hydrogen in the core because it's being fused into helium. So this last graph, this is fairly straightforward. Fraction of luminosity, just how much of the radiant energy is getting out. And the luminosity of the sun, the core produces that energy, but for it to luminesce, it has to get out of the core and then get into the radiative and convection zones to escape the sun. So as a reminder, nuclear fusion is a fusing of atomic nuclei. And when we say nuclei, we're talking about things mostly protons and neutrons. So what we really want to emphasize here is that protons have a positive charge, neutrons have no net charge, and electrons will have a negative charge. So when dealing with these objects, remember that there's these electric forces, and for protons, like charges, that electric force likes to repel them. Let's come here. Let's look at, here I have two protons, right? Proton, proton, and I'm going to try and smash them together. Well, they're going too slow. I'll get this picture where they come near each other, but these electric forces will just repel them away. They're like charges. They don't like being close to each other. So then we speed up. We send them going faster. Okay, they'll get a little bit closer, but the electric force gets stronger. The smaller the distance, the bigger the electric force. So there's this big electric force keeping them away, keeping them far apart. So for fusion to occur, these things need to be going very quickly, very rapidly, until finally they overcome those electric forces, smashing together, fusing. Now, to start building up some comments, some things that we're going to see in this strange world of atomic fusions. Look at the before picture. I have one proton charge, one proton charge. So before the collision, I have a net charge of two positive charges. Look what happens after they've collided, they've fused together. This will be a proton bounded to a neutron. One of these protons is just morphed. One of these protons have just become a neutron. So the net charge of this thing, this nuclei now, is +1. But we started off with +2. We can't just spontaneously make or create, or we can't make or destroy charge. It's just like mass. It's a conserved thing. So if we start off with 2 charges and we have one of the nuclei, the other charge went away as this positron. Many of you have probably heard of an alternate name for a positron. It's called the anti-electron. This thing's antimatter. When you have matter interact with antimatter, you get a huge explosion of energy. Literally, all of the mass of the matter-antimatter pair is annihilated and released as high-energy photons. So, we're going to talk about this picture in a lot more detail in a later video. But I just want you to start thinking about things are getting weird when we're starting to smash particles together.